I'll start 30 seconds early. Hey everybody, my name is Ben. I'm here from Booking. And I would like to talk about two really cool pieces of technology that I've been playing with for the last year and a half or so, and kind of explore where there might be some overlap between them. So Perl 6 and the Zen of Erlang, the philosophy of Erlang when it comes to software reliability. And so some quick context, this is not at all a talk where I tell you this cool thing that I've done in production and you should do it too, and it scales and it's really awesome, yet, maybe someday. This is more about kind of investigating another language community and figuring out things that we might be able to steal, borrow, appropriate, liberate for usage in our own ecosystem. And also to try to kind of boost the signal on some ideas about software reliability that I think are super cool and would, I think, be applicable in other places. So we'll see about time for questions. I'll be delighted to take them. If I don't have time, just find me in the hallway. I'm not an expert, but I will enthusiastically converse about these things. So, yeah. So let's see what we're going to talk about. First off, I want to present to you a unified theory of software reliability. Yes. I'll talk about concurrency in Perl 5 a little bit, about the strategies for managing concurrency in ways that minimize programmer error or vulnerability to programmer error, and then the power of turning it off and back on again. Finally, Erlang and Perl 6. So, we'll start with our theory, our grand unified theory of unreliability. So writing reliable software is easy, right? Like, don't write bugs. Just that's straightforward. So this is, maybe not attainable by everybody. So the other option is write fewer bugs and then try to make sure they don't break everything when they happen. So if we're going to pick between those options, probably we don't have the time or money or skill to not write bugs at all. So we'll try to write fewer and try to make sure they don't break everything. And so to explore kind of something I kind of try to get at the heart of software reliability, I want to kind of propose a counterexample and take you on a maybe scary dream journey into a plausible, hopefully not too familiar situation. So imagine you are a Perl developer somewhere and someone comes to you and says, the sync script is broken. Doesn't matter what it's syncing, user accounts, database backups, whatever. The person who wrote it's not here, vacation, they left the company, whatever. So, okay, you go to investigate and you find on the server where this thing runs, user local bin sync.pl, okay? You crack it open using a program that will not start any editor debates, and and you dive in. Ah. And so you crack open this script, and you're scanning the prelude, the top of the file. And okay, you see there's no shebang, so it's just using whatever Perl is in the path. You do a quick check, it's the system Perl. Okay. You don't see strict at the top. That's a little, okay, like that's not so awesome. You're kind of getting a bit of a sinking feeling, and you start scrolling through the file, and you see some backticks, SSH, remote, Perl, this same script somewhere else. That's a little concerning. And so with this feeling of horror, you decide just on a pure intuition to do a grep for the word sub, and you don't find any. Well, actually, I take that back. You find one thing, and it looks like this. And so at this point, you just roiling with anxiety and unhappiness, you decide to see the scope of this problem, and you scroll to the end of the file, and you find it's about 1,200 lines of this. And so let's talk about your feelings at this moment. So how many of you are feeling some unhappy anxiety pit in your stomach at this thought? Like you've been there, you've had this experience, yeah. How many of you are full of rage, like the hate is flowing through you that you have to deal with this script? Okay. So the first thing is, it's okay. There is still happiness and light and joy in the world. This is just a thought experiment. But I want to explore why so many of us had such a visceral reaction to those symptoms that I just mentioned in that script. Right, yeah. Um, and so is it because this is a case of baby Perl that just got way too big all of a sudden? Is it because it's an unmaintainable script? Well, like, yeah, probably. Is it unreliable? Almost certainly. But I think there's something that kind of connects these symptoms together into a kind of a more abstract classification. And it's the same problem that we see in this picture. Which, yes. So in case you can't see, it's two ends, and the individual bits are soldered together with a soldering wire and then zip tied. So what I want to say is that those things that made us so unhappy about that imaginary script were a case of coupling, right? Excessive coupling, a lack of abstraction. These are kind of the same things. And so when we're looking at a piece of code, like, we kind of have this sense of what is like a good amount of coupling, like things are factored out into subroutines, into classes or not. Variables are declared or not, right? We try to build up these abstractions. We try to decouple things so that we can manage our understanding of the program, so we can eliminate bugs, all that good stuff. And so really when we're talking about coupling, we're talking about the scope of understanding you have to have of that program in order to do something with it productively. In the case of this behemoth, that scope is basically the entire program. Like, any error that happens on any line, lines 1 through 10, lines 11 through 20, everything has to be handled at the top level. There is no sort of fragmentation of responsibility for errors. Everything's right there. And so that's not great, because it means that there's an enormous range of potential problems that have to be dealt with at this top level. And so if we imagine kind of making this a little bit nicer, we maybe have a main sub. For some reason, we calculate pi, and that calls a couple other subs. And then we call sync, and then we finish it up. And so this represents a more factored, we have abstractions. Main doesn't need to care about foo and bar, and that's a good thing. Calc pi, doesn't need to interact with finish. This is all good stuff. If we assume there's no secret global variables, then this is a reasonably well-factored thing that we can work with without having global understanding. However, there is secret coupling in this diagram. And the secret coupling is in these groups. And the nature of that coupling is the fact that this code runs first this, then that. It runs sequentially, just like almost every Perl program, right? And so, first foo, then bar. Calc pi, then sync, then finish. And so in some cases, this is probably the good and proper thing. Like, probably foo should come before bar, because otherwise bar foo, like what? A sync should probably come before finish, because that makes sense. That's logical. But it's possible, maybe even probable, that calc pi doesn't really have a sequential relationship with sync. Maybe it's just another thing this script does for auditing, or for, it's just a background process of some kind. And so because this script runs top to bottom, calc pi is still coupled to, still has a relationship with sync and finish. If it, for some reason, goes into an infinite loop and takes forever, you will never reach sync and finish. If it consumes all the system resources, sync and finish will have a very bad time of things. So they have this sort of time-based relationship. One comes first, the next one comes second. And so if we want to look at decoupling our program to make it more reliable, to make it easier to reason about, I want to explore a different way of thinking about a different axis on which we can decouple, and that is temporal decoupling, right? So not everything needs to run top to bottom in a straight line linearly. And so why would we think about doing this? Well, just for the same reasons we would decouple anything, which is to break things into smaller pieces so we can reason about them, they can be simpler. To have an interface between our different components, just like we'd have a class that interacts with other classes over a defined API. And so that we can kind of minimize the scope of errors that each component needs to deal with. And so this probably sounds a lot like concurrency, and you're right. That's what I'm talking about here. And the key property is, for some things, I don't care if they run at the same time or if they run at different times. And like lots of places in software development, if there's a guarantee that we don't need, it's probably, like when we have a guarantee about order, it's probably costing us something. And so if we can give up that guarantee, we might be able to gain something back in exchange. And so what I'm proposing is that when you can give up the guarantee of software running linearly, you might be able to gain some reliability. So, but if we're going to talk about concurrency, I want to stick with something familiar. I think we are mostly Perl 5 programmers, at least were at some point. So let's explore what concurrency looks like in Perl 5. And typically, that involves looking at our extremely rich ecosystem of event loops. So let's write one. Let's add more, right? So that kind of covers our theory of unreliability. We're talking about coupling. Let's look at concurrency and temporal decoupling in Perl 5 using event loops. So we're just going to go through a really quick select-based implementation of an event loop, just so we all are totally clear what is going on inside of any event, inside of Mojo IO loop, inside of Po. And so, as it turns out, event loop is totally literal. Like, it is just a while loop at the heart of things. It uses this special object select, which has a bucket of sockets, and it just has some of them that are ready to read and some of them that are ready to write. And that's it. Our loop has to address both of these things. So we'll start looking at the ones that are ready to write. So we go through all the ones that are ready to write. We write something to them. Hi there, right? And so now we have a very scalable network service for greeting people. For the sockets that we want to read data from, it's the same thing. If the socket that's ready to read is the one that we're accepting connections on, then we should accept that connection and add it to the pool of sockets that we are selecting on to see if those connections we just accepted should write some data, read some data, right? If it's not that, if it's a client connection, then let's read some data. If it sounds simple, it's because it is. This is not complicated stuff. We'll print some data that we got from the client. So it said something, we'll just print it out, spit out. Great. If the sysread fails and we didn't get anything, then it's probably time to close the socket and take it out of our pool. And so that is an extremely simple but complete event loop. And so you might be wondering where the events are in our event loop here. Well, instead of just printing out the data we got from the client, we'd probably fire off some callback for onRead. And we might register a whole bunch of callbacks for different sockets, or many of them might subscribe to the same socket callback for onRead. And that's fine. We would just call a bunch of subs, and we would trigger everything that wanted to find out when we got some data would get the data. That's great. Same thing for onClose, and then same thing for onWrite. And so folks who have done a little bit of event loop programming have probably recognized the names of these callbacks because they're fairly standard. The API doesn't differ that much between the different event loop implementations. And so, but the key point is that because this is still a loop under the hood, no matter how pretty the API is for any event or IO async or using promises or futures or whatever, if you put something in the loop that stops the loop stops, right? So all the clients that are using that loop will also stop because it's just a loop. And so sleep is a fairly extreme example, but also querying something from a database because DBI has a blocking interface. And so if you send off a really complicated query in the middle of your event loop for one client, every client that's in that event loop is going to pause while you wait to hear back from the database. And that's just how a DBI works. So to take a quick poll of the room, folks who have written event loop-based code, would you say that using an event loop made your code simpler? Raise your hand if you made your code simpler. Yep, okay, right, one person. Would it say you made your code faster? You had an IO-bound workload, and so you got really big gains in efficiency. Okay, yep. Would you say it made your code more reliable, like more fault-tolerant? Okay, I'll just stop there. Would it say you made your code more scalable, so better hardware utilization for the amount of, yeah, okay, yeah, cool. So basically, for us as Perl programmers, broadly speaking, when we think about concurrency, we're thinking about an optimization. And like lots of optimizations, event loops are fragile but fast. And so because they're an optimization, I don't think this is surprising, event loops don't do a very good job of accomplishing this sort of temporal decoupling that we're interested in order to get these reliability gains. They don't really decouple very much. They're kind of a leaky abstraction on top of the idea of concurrency. So I posit that this holds even when you're using one of the nice APIs, so you don't have callback mountain. If you're using promises or futures or other concurrency things I've never heard of. If they're based on an event loop, the same restriction holds true. If you block, everything stops. And so why is it that this is a poor, why is it that this kind of concurrency doesn't help us satisfy that notion of temporal decoupling, of taking our program into different pieces so it can be more reliable? And so that takes us out of the realm of juggling raptors, about Perl 5 concurrency, and into types of concurrency. And so now we're going to talk about schedulers. So basically, there are two kind of broad categories of schedulers when we're talking about concurrency. You have cooperative and preemptive. So cooperative schedulers, event loops are in this category. So are coroutines like Coro or Python generators or Lua coroutines. And the defining characteristic of all of these things is that the programmer must explicitly yield when they are done doing their work. So like in an event loop, this might be calling a callback. I'm done my work, next thing can do its work. It might be calling promise on a promise or calling done on a future. You have to explicitly give the CPU back when you're done with it. If you don't, if you sleep, if you call a blocking DBI call, nothing else can do its work in the meantime. And so what that means is that a single bad actor anywhere in your system, if you have one bug in your code, it will affect everybody who is connected to your program. And that's maybe not so awesome. And so a preemptive scheduler, it sounds kind of exotic, but actually everyone's really familiar with this because this is how operating systems schedule processes. Except with the minor exception of Windows before 95 and Mac before OS X. So in those cases, if you wrote a bad program, you could lock the whole system and nothing would happen. But thankfully, everyone has improved since then. Basically, all modern operating systems are preemptively scheduled. The same goes for threads. So if I fire up 10 threads and I'm doing things, the operating system will pick and choose which one of those gets to spend time on the CPU. And the important thing is that user code has next to no say in this matter. Even if I'm a programmer who's writing really silly blocking code, the CPU, the operating system scheduler will say, this thread has had enough time, I'm going to pick it up, put it elsewhere, something else gets time to execute. And so the scheduler is the boss, and this protects you from a whole category of kind of programmer errors. And so I think a fairly apt analogy when we're talking about concurrency and different kinds of schedulers is, the kind of one way to think about the relationship between cooperative and preemptive is the relationship between using malloc and free and garbage collectors. And so a cooperative scheduler is really fast when it's correct, and it's pretty simple to implement. I just showed you a Perl implementation in 20 or so lines, and they're fragile. They are really vulnerable to programmer error. Same thing with garbage collection and preemptive schedulers. They tend to be slower, lower throughput, because the scheduler has overhead. It has to make decisions about when things are on the CPU and off the CPU. The implementation tends to be complicated, at least compared to cooperative schedulers. But it has this property where it's pretty resilient to programmers making mistakes. And I don't know about you, but I like it when things take care of my mistakes. And I think lots of us actually come down on this side of the trade-off where we're okay with code being a little slower, a little more complicated behind the scenes, as long as it fixes my mistakes, right? We are, Perl, broadly speaking, that family is very much in this tradition. So, okay, since threads are preemptively scheduled, let's look at that. Let's write a little reliable program using threads. So let's go back to our sync script. We have calcpy and sync and finish. We can kind of put calcpy in its own thread. We can put sync and finish in another thread. This is great. If calcpy blows up or has some problem, that's fine. It won't bother sync and finish. This is great. And yeah, but maybe not. Maybe threads are not actually what we want if we're interested in writing really reliable programs. And so let's explore that a little bit. So if our goal is to decouple pieces of our program so that they don't have this implicit time-based relationship, and the reason we want to achieve that goal is so we can have simpler components so that we can enforce the interfaces between them, so we can make the individual components more reliable, well, threads might not do everything we need there. And so one of those problems is that there are limits on the number of threads you can have. And now these limits are high. If you ever bump into them, you're probably doing something radically wrong. But the fact that the limit exists is kind of suggestive. And so if you go poke into procsys kernel threads max, you'll see a number. And on the VM I was on, it was about 8,000. And so, okay, that's an obscene number of threads if you're writing a program that's using that many threads. However, if you think about this from the perspective of decoupling your code into sensible concurrent components, imagine you were writing a system and someone said, so that's fine, write your classes, but make sure you never use more than 7,744 objects or nothing will work. Like that's kind of weird, right? Like, I don't want to have to think about that when I'm deciding when I use objects or not. I want the amount of objects in my system to suit my problem domain. So, okay, that's not so awesome. In terms of decoupling, well, threads probably hurt more than they help. In terms of simplicity, we are suddenly thrown into this world of locks and atomics and thread-safe queues and race conditions, all kinds of horrific things. In terms of respecting interfaces, well, threads by design have access to the entire memory space that my process is in, so they can just access whatever they want, right? There's not really any guarantee that they're restricted to the areas that I want them to be, to like the rich data they're touching. In terms of reliability, threads are unsafe to terminate arbitrarily and also unsafe to restart because you don't know what state they were in when they turned off, and you don't know what state what state they started with when you first spawned the thread, or whether that's still an appropriate state to start them in. And so that's kind of weird. Like, you know, if you go look on Stack Overflow and you look for someone saying, how do I abort a thread? Everyone will say, no, stop, don't. That's a terrible idea. You should never do it. And they're right, because you're basically picking a line of code and saying, ep, and you're broken. And how your program copes with that is entirely unpredictable. But this is actually a really valuable property if we could have pieces of our code able to terminate and restart safely. So let's look at that, the power of power cycling. So turning it off and back on again is like the magic incantation for all software problems, right? Like, you know, probably if I had spent 2 more minutes and turned my laptop off and back on again, the projector would have worked instantly, right? This is universal, and we all have this intuition after long experience. And so it's interesting to think about, why is restarting so unreasonably effective? Why does it solve so many problems so well? Well, so I'm going to borrow from the talk which inspired this one, called the Zen of Erlang, and he discusses these classifications of bugs. This also goes back to, what was it, the tandem nonstop systems. One of the authors wrote about this distinction in bugs. So you have bugs that happen every time you run some code path, and we'll call those Bohr bugs. These are easy to reproduce because every time you hit that piece of code, they happen, and so you can fix them. Some bugs happen never, or only sometimes, and those are Heisenbugs, and we all love those, right? They are impossible, they are maddening to reproduce, and therefore equally maddening to try to resolve. And so when we're thinking about why restarting is so good at dealing with errors, especially transient errors, it's worth looking at this classification. Because Bohr bugs happen every time, like I have an error in my config file, turning my program off and back on is not going to help. It's just going to crash again right in my face. However, because it happens every time, I probably should have caught it before I pushed it to production. Like if I'm developing a program and I have a typo in my config file and it just fails to start, that's kind of on me if I push that into prod, right? However, Heisenbugs are much sneakier, and because they happen almost never, they depend on the stars aligning in just the wrong, horrific way. Restarting is actually a really powerful strategy for dealing with these errors, because the stars have misaligned, and now things are okay, I can make progress. And so the thing about Heisenbugs happening almost never is, the definition of almost never is very different for what's in your development environment versus what's in production. So you can have a bug that is impossible to reproduce in dev, really hard to track down, but when you get 10,000 requests a second on this system, it might happen a minute every 30 seconds, right? And so it's kind of where you start making a cost-benefit analysis. Do I want to just turn the thing off and back on again, and then it'll be okay, or do I want to invest the weeks of my life to hunt down why this is broken? And so there's a really powerful idea in this notion of why restarting is so good, and the idea is that you can have a reliable system that isn't error-free. Like, you can have bugs in your system and still have it be highly reliable, as long as you tolerate them, as long as you know how to deal with them. And so it would be really cool to incorporate that in the way we write code. Can we do this thing? Well, the answer is we do this all the time because this is how operating systems work. Because operating systems are awesome. They're really powerful. And they do all the things we've been talking about so far. They have preemptively scheduled, no shared state, isolated, safe to kill, safe to restart units of concurrency, also known as processes. Like all of those properties apply to an operating system process. And we're really familiar with that because that's what we do. And so the cool thing is because these things are isolated and no shared state, they're safe to restart. And so we can construct this sort of tree of reliability where we have init at the top, maybe some supervisors in the middle, and at the bottom we have our workers, either web workers or cron or SSHD or whatever. And if cron, blows up, init will restart it. That's great. It's handled. And so that's okay. We're fine if one of our web workers crashes or if SSHD flips out for some crazy reason, because init will bring it back up. We're much more concerned if there's a problem in init, because now we're kind of piercing into the core of our tree of reliability if we're approaching the root. So, but the thing is, we can only use this at the granularity of an operating system process. And as we write more sophisticated programs, the amount of state and logic and stuff happening inside a single process can be very substantial. So it would be nice if we could use this at a finer granularity. And this is where we're going to talk about Erlang. So, the blurb for Erlang, I'm sure folks have bumped into it, a general purpose concurrent language, functional language. I'm going to hype a little bit because I think it's really cool. It probably runs stuff on your telephone. It probably provides services. It's very reliable, broadly speaking. Some people say 9 nines. That's probably optimistic, but 5 is reasonable. That's still a lot of 9s. There are folks who are running it in production that have millions of sockets connected to a single server. WhatsApp famously had 2 million for a while, and they're like, yeah, it's kind of too many. We're going to scale that back just to have better, spreading out of the load. But it was fine. The server could cope. The other really cool, really unique thing is that different servers, there's built-in coordination, kind of like Zookeeper or ZeroMQ, that's just as part of the platform layer. So you can just send messages to different parts of your Erlang cluster. That's really neat. And maybe most importantly, it's older than Perl. So it's really mature. This is not like fancy, shiny technology by 1 year, just by a little bit. So these ideas are not necessarily brand new, and they're definitely well tested in production and reliable services. And so there's basically, I think, one kind of key insight in what makes Erlang really interesting, and it has to do with this notion of kind of a hierarchy of how coupled things are. And so I'll go through this, so like lines of code, one to another, have a fairly tight coupling. Like one runs after the other. They probably share some variables, some state. Functions and classes are a little bit less coupled because they can be broken apart. They have defined APIs. Threads are even more decoupled because they can run at different times, but maybe not entirely clear because they're still in the same memory space. Child processes that are forked are a little bit more independent than threads because they don't share memory. Processes on the OS don't have a common parent except for init, so they're even a little bit more removed. You can talk about operating system virtualization, so things are even more independent, and then network services, and then even whole systems. And you kind of have this increasing scale of how decoupled the bits are from each other. And that's fine. And the interesting thing about Erlang is it recognizes that kind of concurrency and reliability are two sides of the same idea. They're the same coin. Because pieces need to fail and be restarted without breaking the rest of your system, just like on an operating system. Operating systems do this. And so the really powerful idea in Erlang is that it takes things that happen at this layer and it applies them to this layer, functions and classes. So no longer do we have this kind of monolithic chunk of functionality. We can break our program into very small pieces, as small as a function, and run it with the same set of kind of independence and reliability guarantees as we get on the operating system level for an entire process. So Erlang, the operating system, is maybe a better way to think about it instead of a programming language. And it calls its units of concurrency processes. This is very unhelpful when you're teaching people about it. But they're not operating system processes, they're green processes. That is, many, many, many of them are scheduled onto the same thread together. Erlang implements a preemptive scheduler on top of the operating system. The memory of these green processes is isolated from each other. They can't step on each other's toes. They're preemptively scheduled, and most importantly, they're safe to kill and they're safe to restart. And so what that means is we can do really cool things very similar to what the operating system does. So if we look at how we can structure a program using these ideas, so here's the same sync.pl, and this is a tree, and like maybe a tree is not the most normal way of representing our code in Perl, but in an operating system, a tree is totally the normal way of looking at our processes. Here's PS tree, right? And so in Erlang, here is an organization of a small program. And again, it's organized into this hierarchical supervisors and workers relationship. And what this enables is this notion of let it crash, which is what all the Erlang advocates are so excited about, right? But we do the same thing with operating systems. Like if SSHD explodes, init has it covered. That's totally fine. It will restart and everything will be okay. And my Node.js server doesn't even care. It's fine. SSHD went away, it came back, all was well. So that's a really powerful idea, and the same thing applies in Erlang. So if we have some random worker, we can pretend it's equivalent to SSHD on an operating system. We have some supervisor, kind of like init or supervisor D. If my thing crashes, well, I just restart it, bring it back up, and that's fine. And this other random thing in my system doesn't have to care that something just went wrong elsewhere. This is incredibly powerful because it means that you don't have to spend as much time writing error handling code in your workers. Because, let's say, my web worker in my Perl script is running under UWSGI or Starman or something, if I have an error in my Perl code, that's okay if it's more fragile, as long as the thing that's running it is solid and can tolerate that failure and start it back up. And so the same thing here, where my edges, like my workers, they don't have to. It's okay if they break, because they'll just get turned back on in a safe way. And so all the code that I would normally write to be defensive about different error conditions just kind of merges into, am I okay with this thing turning off and then back on? And a lot of the time, you are okay with that, and that's really cool. So that's some of the Zen of Erlang. How does it apply to Perl 6? So Perl 6 and concurrency is very different from Perl 5 because it has real threads, not pretend threads. But threads are kind of tricky to build on. So the primitives in Perl 6 are higher level than just threads and walks and such. We have a couple of basic things. You have supplies, which are just events. Like many things can subscribe to them, something can publish, all the subscribers will be notified. That's cool. We have channels. These are thread-safe blocking queues. Just like in any other kind of, like, very similar to Go channels, very similar to thread-safe queues in other platforms. And then we have promises, which are a little bit unique and maybe remind a little bit of Erlang processes, because they are this little chunk of asynchronous computation. They're a function that we said, we'll run this asynchronously. So because they encapsulate some chunk of code, they encapsulate it entirely. So a failure inside that piece of code is totally fine. Like I can die, I can all kinds of horrible things inside my promise, and that isn't going to propagate to the rest of my system. The error ends up being accessible through the result of the promise. So you can pick it out whenever you're interested in it, and this is really cool. And maybe I can do some blocking operations inside them. I'm going to show you right now the degree to which you can treat them like processes on the operating system or in Erlang, or the degree to which you have to kind of think about them like event loops. So now, danger mode, live demo. All right, cool. So that is hard to read. Color scheme, let's do summer. Is that easier to read? A little better, maybe? Margin. Sorry, futz. Okay, great. So, same color scheme problem. Okie dokie, so. Can you make it larger? Yes, definitely. Plus. How's that? Plus? There we go. Yeah, cool, okay. So this is a really simple program, right? So I have a start time, I have an array of promises, I want to say, hey, I'm about to do some work. I go a loop up to 3, and then in each iteration of the loop I start a promise that sleeps for 3 seconds, and then at the end of 3 seconds it says, okay, I'm done, and that's it. So here. It starts, it runs. We wait for about 3 seconds, and then great. So this is cool, because if I were to do this in an event loop using futures or something, that would be a 9-second operation. So these things are not blocking each other, basically. However, if we switch to a slight variation of the same program, and we ignore my syntax error earlier, instead, let's now move up to 17 promises instead of 3. And so when we run this code, we do the same thing. Otherwise, it's identical, right? So we move through 15 of them, or 16 of them, and then finally the last one kicks, and we run the whole thing in 6 seconds. And so what's happening here is that promises are not actually preemptively scheduled, nor were they ever claimed to be. I just thought they were for some reason. They're put on a thread pool, and so a promise runs on a single thread. And the default thread pool size is 16. So when I bumped up to 17, I filled up my thread pool with promises that were all sleeping, all blocking, and then my 17th one couldn't do anything until at least one of those finished and a spot opened up in my thread pool. Back to that. Yeah. So concurrent sleep shows us that it's not the same as an operating system process. Yes, Liz? Cool.
But you want to apply that to all blocking.
Yeah, exactly. So, okay. So it's a thread pool, and so promises are basically cooperatively scheduled on the function returning from the promise, and that's when they yield the thread back. And so the trouble with using this to try to structure our program kind of along the bounds of its natural contours in terms of which things need to run concurrently and which ones don't, is that the degree to which you can do that is directly related to the size of your thread pool. So just like before when I said, Linux limits you to, 7,000 something threads by default, the limit of the size of the thread pool, even if you made it really large, still kind of, it discourages you from using this as a way to shape your program. The other piece of it is that they have sort of similar caveats to threads, where because they share state with each other, they're not isolated like operating system processes or Erlang processes. They're just closures. There's no way to know when it's safe to turn them off or to restart them. Like this notion of let it crash and then just turn it back on isn't really applicable, because you don't necessarily still have the state that you needed to start the promise. So basically what this boils down to is there aren't that many of the ideas in Erlang that can be kind of directly applied to Perl 6 in terms of software reliability, at least as it seems to me. As long as promises are still closures, this is probably not likely to change substantially. However, like Liz mentioned, there are languages that do have much kind of more flexible concurrency approaches. One of those is Go. And so Go routines and promises actually have extremely similar semantics because they're both closures. They both are just wrapping over their current scope. In Go, however, everything is entirely preemptively scheduled rather than mapped to a thread pool. So you could have, 1 million Go routines on my thread pool of 4 schedulers or whatever, and they would just all get scheduled around by the scheduler. And so this is more resilient to programmer error than just a thread pool and accidental blocking. But it's still not quite the same as what we get with an operating system process or an Erlang process, because really what we're talking about with, say, Go routines or even promises to a degree is sort of cheap threads. Like you can have lots of them, and that's nice, but it doesn't really get you the degree of kind of interface restriction or fault isolation that you see with operating system processes or Erlang ones. You could, in theory, I think, build a preemptive scheduler into Perl 6 for promises. This would be a huge amount of work, but I think the semantics would stay the same. I think there's nothing that depends on it being a thread pool as far as I can understand. So this sounds a little negative. I am totally honest. This is not the talk I expected to be giving when I wrote this proposal. I was really excited about Erlang and Elixir, which I'd been playing with a whole lot, and I knew from playing with Perl 6 that I could have things that ran concurrently that did blocking operations, and I basically hadn't run enough of them to max out the thread pool. And so that was silly of me, of course, but this was a good exercise in kind of digging into the exact degree to which that is the case. And so maybe it's not a terrible thing. Like Erlang is a very specialized language compared to Perl 6. You can't just mutate the grammar at will and invent postfix operators. Like that's not a part of Erlang. And moreover, not everybody is writing network services, which is really kind of the sweet spot for Erlang and other Erlang VM languages. That said, lots of us are writing network services, either in the form of web applications or other stuff. And so I don't want to close by kind of condemning Perl 6's concurrency because it is still great. It is so much better than what we have in Perl 5. And it is very similar to the tools that have been used in, say, C#, .NET, and Java really effectively for a long time. It's just oriented kind of differently from what we see in an operating system or in Erlang. So that's it. Thank you very much. Thanks, Perl 6, for answering my questions. Yeah. I think we have some time for questions. Okay. Cool. Okay. I mean, I can go show some Elixir code, the thing with the tree and the observer, if you want that. But I cut some content because I was worried about time. So, are there any questions before? Yeah.
Yeah. So I think this is my misunderstanding, but I thought that Go schedule wasn't preemptive. I thought it was cooperative because the runtime and the compiler check for like sleeps and the switch statements and
Mhm.
select statements, and then actually do a yield on the runtime to yield back that.
Yep. Well, so the question was, isn't Golang scheduler actually a cooperative scheduler? And to some degree, I think you get into kind of fuzzy territory because if the runtime basically yields for you and I don't have to think about it as a programmer, then the end effect is that it is effectively a preemptive scheduler from my perspective as a programmer. That said, Go preempts on memory allocation and function calls. And and a couple of them. And so it's like, I think there's a bug open that's like, the scheduler isn't fully preemptive and we should fix that someday. So yeah, I think it appears preemptive to the user, even if it's maybe not, maybe not every single operation can be preempted at the language layer.
Basically, nothing ever blocks. It's just false.
Yeah.
And let me just say that, that is really the end goal of the current scheduler is really a prototype.
Yeah, I mean, we're
Very nice. We've had Erlang in our sites for
good.
years now.
Cool. Yeah.
So from what you said about init being the top of the tree of reliability,
Mhm.
I think the obvious implication is that the other thing to do would be to make init as complicated as possible. A lot of functionality.
Ba-dum, tsh. Yeah, sorry. So the question was, systemd is complicated. It shouldn't be in it. Is that a fair summation? Oh, sorry. I was not accurate. Yeah, Liz?
So, like everything else in Perl 6, the schedule is actually pluggable. And so you can, I think it's well clear for you that.
So I did actually look into this when I was starting to play around and kind of first ran into the thread pool limit, and I was like, oh gosh, should I write a preemptive scheduler before YAPC? The answer was no. That would have been a bad plan. Right, exactly. And so I think the trouble is that at the Perl 6 layer, like, you need VM support. Like, I think more VM would have to change in order to be able to support a fully preemptive. Yeah.
That's open source too.
That's true.
You're grading yourself deeper. You can actually just create your own thread pool schedule with another maximum thread.
Yeah, absolutely. So like certainly you can tune the size of the thread pool. And I think for many situations, that's totally fine. Like if you're not trying to write Erlang in Perl 6, you probably won't have this problem, right?
The other point to make here is that about your state outside, not being able to restart, you can voluntarily restrict your access to outside
Yes.
state and use the known safe primitives to communicate between these things, and then that together with a restarter would be pretty
Absolutely.
But it would still be voluntary, it would not be enforced as.
Yeah, exactly.
everybody does. But that's arguably one of the reasons it's not very beginner friendly.
Absolutely. Yes, totally agree.
So one thing, with Erlang, the other thing, like you mentioned, Larry, is the state is always refreshed every time it recalls that function.
Mhm.
So the VM is able to hold that state. So when it crashes, it's able to restart from that last state. And I
Mhm.
don't think you can get that with closure because the packet came into it.
Yeah. So the question was Erlang, when you have a process, basically you can think of it as a recursive function, and it carries sort of a state hash or data structure with it from every call of the recursive function. And so when it crashes, the VM still has the state, and so it might be able to kind of pick up and call the recursive function at the point where it was with the same collection of accumulated state. But when you have a closure, that's less safe. And the same goes for Go. Like, you can't restart a Go routine arbitrarily. So I think similar to Perl-6 process in that regard, or promise. Yeah. Oh, yeah.
So your implementation and your administration is very interesting because most of the time I see that coupled with basically a thread pool and closure that informs the operation as another mutator on the event loops to write that asynchronously.
Okay. Yeah.
And so it kind of borrows some of the ideas from both worlds.
Yeah, absolutely. I mean, and so even things, so the question was about, like in many practical implementations of event loops, they actually use a thread pool in order to avoid blocking the event loop for things that would normally block. Is that a fair summary? So this is like what Node.js does, for example, because not all syscalls are non-blocking. And so sometimes you need a thread to do a blocking operation, but you can't stall the whole loop to do it. And so, yeah, Node does this, Go does this, Erlang also does this. They all have a thread that's dedicated to calling a system call that would normally block everything, and they just do it in a different thread. So, okay. Cool. Okay. Thanks very much.